Welcome everyone. This is Jim Chastain. Welcome to the Thursday webinar, and today we have as our guest speaker an EasyPower expert on alternative energy and bulk electrical systems. And before I introduce him, I would like to conduct a poll question, and we would appreciate your feedback via these polls. There's no obligation, but certainly we appreciate your attendance. And the first one is about your involvement with alternative energy designs to start with. So how many systems do you work on a year, if you would please? So it looks like we've got a quorum here and a few late arrivals, but again, welcome everyone. So here's how everyone has weighed in on this question. Looks like most folks are doing smaller systems, which is good. And then the next question is, what's a typical size of a system that you work on? And kind of expect this one to vary all over the map. We have been getting a lot of inquiries and questions about alternative energy designs recently, which is not surprising. So I think that's why the interest in this particular webinar has been so high. So it looks like we have most people joining in. So we're going to close this one out. Hopefully you got a chance to participate. It looks about 50-50 between less than 1 megawatt and greater. And then our final question is, what type of analysis do these usually require? And obviously that's a soft spot in our hearts. As we advertised on the announcement for this webinar, we don't suggest this is necessarily for beginners, a topic for beginners, but I enjoy it. And so hopefully you will. It's certainly, there's no prerequisite as far as attending, but I think understanding the focus of where we're going applies to all sizes of designs. So here's how people weighed in on this one. Frankly, that's kind of what we were hoping for as far as this distribution. So anyway, let's get on to the material. As I mentioned, Tao Yang is one of our in-house experts on alternative energy and bulk electrical system evaluation and analysis. We have pre-recorded this presentation, so Tao is on the line with me and can answer questions real time. So by all means, take advantage of that. And I hope you enjoy the presentation.
Thank you, Jim. Good morning or good afternoon, depending on the time you watch this webinar. The topic of this webinar is to provide an introduction or refresher of the method to equivalize solar wind farm EasyPower one-line design to bulk electric system or large-scale study model. Let me first introduce myself. My name is Tao Yang, and I'm the principal engineer in EasyPower. I've been working in the utility industry for over 10 years on power system operation and planning, focusing on power flow, short circuit, stability, harmonics, EMTP studies, and smart grid applications, such as synchrophasor. Renewable energy has been a popular topic in the past decade, and you can see that more and more states are targeting at 100% renewable generation. So the design, development, and the grid interconnection studies of the PV solar and wind farms are becoming a critical topic to the power and the utility industry. At the utility scale solar farm design stage, different models from different software platforms are used for different study purposes. For example, most of the EasyPower users would use EasyPower to design the solar farm one line and perform relay coordination and arc flash studies. But if there is a need to interact with the utility or RTO/ISO regarding grid interconnection studies. The large-scale system study may require lumped or equivalenced model derived from one-lines. Sometimes equivalencing those one-line designs to lumped model might take some time and engineering judgment. And that's why we want to do this webinar to refresh the method of how to equivalize the EasyPower one-line to a BES level study model. Expectations, what do we want to get out of this webinar? I'm expecting that after this webinar, we can refresh our mind about how a solar farm or a wind farm one-line design looks like. We are able to understand or even explain the theory of equivalizing, and being able to develop equivalized model from an EasyPower one-line. With the expectations laid out, we will first review some practical one-line designs to understand how a PV solar farm or wind farm one-line looks like, and then how the BES level study model is required to be. At last, we will use the power loss-based equivalizing method to link them together, which includes the theory and implementation of equivalizing the one-line design into a lumped model used in the BES level studies. So after that, we will switch from the presentation to a live example or live demonstration to use a 20 inverters, 40 megawatt solar farm as an example, and we will demonstrate how we equivalize this one line to a BES study level model. After that, we will introduce some topics about inverter turbine grouping. As you can see, if we have 20 inverters, 40 megawatt solar farm, which implies that each inverter would take 2 megawatts or generate 2 megawatts, we have the same size of inverters throughout the plant. But most likely it's not the case in the real world. We usually have different size of inverters in the same plant. So in that case, we have to group different size of inverters to use different equivalent. That's a topic we'll talk about at the end. Now let's first take a look at the solar farm one-line representation. So from the grid interconnection perspective, the rule of thumb is that only the equipment can be seen by or interact with the AC power grid is required to be modeled in the BES studies. So that's just a rule of thumb. And with that rule of thumb, you can see that I didn't model my inverter as a solar panel and inverter as we usually do in EasyPower. Instead, I only use a generator to model the inverter, and I may not care too much about what's beyond my inverter. It can be a solar panel, it can be a Type 4 wind turbine, it can even be an energy storage, because I only care about how the inverter behaves, how the inverter interacts with my grid, right? So I can use a generator to represent. And from the generator, I have a pad mount transformer. Some people call it as GSU as well, to go up to the collector system level from 0.69 kV usually to the 34.5 kV. And at the 34.5 kV, I will use my collector system to connect each of the inverters together radially. You can see from this design, the farthest is collector 5A, and it would go through the collector system all the way, I'm sorry, click on the wrong place, all the way back to where the low end of the main power transformer is. Some people call this main power transformer as the substation transformer or the utility transformer, depends on the nomenclature. Now that's basically the one-line design of a solar farm or wind farm if you replace the generator from inverter to Type 3 wind turbines. What does a BES model take? By comparing this BES model with the previous one line, you can see that the interconnection transmission line, aka gen-tie line, is explicitly modeled. The station transformer, aka MPT, main power transformer, is also explicitly modeled. And if you have any plant level reactive compensation devices, it would also be explicitly modeled. However, you won't model the collector system in detail. You won't model every piece of your pad mount transformer and the PV system in detail. Instead, you would use the equivalent to represent the whole system. So you have collector system equivalent to represent your collector system, which consists of many circuits. You have a lumped pad mount transformer equivalent to represent all the pad mount transformer used in the plant. And you will have only one generator to represent all the generators/inverters in your plant. Why? Why the utility cannot just take my one line and move forward from that point and ask me for an equivalized system? This is because if you think from the utility scale or transmission level study, all the generators connected to the transmission grid would be put in one case and studied together. Now, at the transmission level, if you think the United States as an example, you have Western interconnection, you have Eastern interconnection, and the Texas interconnection, which is ERCOT. So especially in the Eastern interconnection, you have, I would say, tens of thousands of generators connected to the grid, needs to be studied in one file, in one case, including power flow, short circuit, and stability. So having more than 10,000 generators, or even more generators in the same case and study is a big task of work. And sometimes if you need to model every solar farm or wind farm in detail, such as one line, you may run out of bus numbers or bus names, right? Because you can see from the one line before, you have 5 generators and more than 10 buses used to model it. And instead, in the equivalized model, you can see that there will be only 3 buses and 1 generator used to model it. So if you model every plant in detail, you may run out of space, and that would severely drag down the performance of the simulation. And that's my take on why. So we have to provide a utility equivalized model and which can accurately represent your plant as well to perform their utility scale large system studies. That's my take on. Now, how could we do that? By comparing the one line we have on the left-hand side and the equivalized model on the right-hand side, we know that we don't have to worry about the main power transformer. We just need to build equivalized circuit for collector system, pad mount or GSU, and inverter. So we call the collector system equivalent as the equivalized collector system. And we have pad mount equivalent, inverter equivalent, or generator equivalent. We will introduce procedural steps for each one of them. And the collector system equivalent is the most comprehensive one, so let's start from that. Please bear with me because sometimes this is a little bit overcomplicated to understand if this is the first time you touch this. And we will introduce both the theory and the implementation of how to make that happen. If you follow me, and I guarantee you will can understand everything within this webinar. The method used to equivalize the collector system is called as power loss-based equivalizing. The principle of this method is that the total amount of power loss from your one-line design should be equal to the total amount of power loss from your equivalized system. So that's just the principle. And if we look at the final equation derived from that principle, you can see that the equivalized collector system impedance is just some weighted average of each collector circuit. Suppose here, for circuit M, you have upstream power flowing through this circuit, right, from your radial connection. The impedance of the circuit is Zm. So the total loss can be represented by the sum product of P squared and Z. If you divide that by the total power flowing through the equivalized circuit, that gives you the impedance. Hopefully, that's straightforward enough, and we will discuss about the details in the later on slides. For the line charging, it's different because if you look at the collector system, you can imagine the charging as a bunch of capacitors connect in parallel. So in that case, the total charging of all your collector system is the sum of line charger of each collector. So suppose you have n number of collector circuits, the total charging of your equivalized collector system would be equal to the sum of each circuit line charging. All right? So charging is easy to understand. Line impedance, let's look into details about how the equation is derived. We know that we need to calculate the loss and make sure the loss total is the same. So let's start from the loss equation. How to calculate the loss of a circuit. So loss is equal to the delta V, which is a voltage drop on this circuit, times the current conjugate, right? That's basically the active power, apparent power calculation equation. Now, delta V can be represented by the IM times Zn, which is the current flowing through the circuit, times the impedance of the circuit. And we know that IM can be written in the way of the conjugate of apparent power, Sm, divided by the voltage, V. If we make simple assumption here that the power flowing through the circuit has a unity power factor, then we can get rid of the conjugate sign by replacing the Sm with Pm. Now the Pm becomes a real number, and V can always be represented as by 1 with degree 0. So you don't have any imaginary part at all. So you get rid of the conjugate sign, and the total loss on this circuit would be the active power flowing through this circuit square divided by the voltage square times the impedance. So the total loss from your one line would be the sum of all the circuit loss. Apply the same circuit story to the lumped equivalent circuit. You can see that the total power flowing through the circuit is P total square, right? Divided by the voltage square times the impedance of your collector system equivalent. Now that's the loss on the collector system equivalent. That should be equal to the system total loss, which is the sum of the Pm squared divided by V squared times the Zm for each circuit. So that's how we come up with this equation. And if we keep assuming that the flat voltage profile is flat, which means that the V squared on the left-hand side of the equation equals to the V squared on the right-hand side, we derive the collector system equivalent impedance is equal to the sum product of P squared and the impedance Zm on each circuit divided by the P total square. So that's the process of deriving this equation. Implementation. Let's take a simple example. Using the same one line we used before, that we use 2 megawatt 2.2 MVA as my inverter, and I have 5 collector circuit to connect each inverter together using a radial connectivity, right? From the low side of my MPT, go 1, 2, 3, 4, 5 levels. Now I have my 5 circuits, and then I can know that from my farthest circuit, which is circuit 1, I have 2 megawatt. Going one closer to the substation transformer, I have 4 megawatt, 6, 8, 10. So the equivalized impedance of the collector system equivalent would be the sum product of P squared times the impedance. Actually, the sum product of P squared and Z divided by the P total. And my charging of my collector system equivalent is actually the sum of all the charging of all the circuits, right? Straightforward. So we keep in mind about those equations because we're going to use them later. What we need is the impedance of each circuit, which makes sense, and the active power flowing through the circuit. If we have to gather information of those two quantities, and then we can get our impedance of our collector system equivalent. Now, about Pad-on transformer and the GSU equivalent, the theory is much simpler. You can just imagine that the equivalent transformer is just the transformer equivalized by a series of parallel connected transformers, right? So if you have, let's say, 5 transformers connecting parallel, so the impedance would be 1/5 of the impedance of each one of them. And if we recall our per unit theory, that we don't have to change the impedance, we just need to raise the MVA base of the transformer by n times. N is the number of transformers connecting parallel. Then I got my parallel transformer equivalent, right? Same story applied to generators. For the synchronous impedance, transient impedance, and subtransient impedance, I can do the same thing. I don't have to change the per unit quantity, but just raise up the generator MVA base to the n times the single generator MVA base. Then I got my equivalent, because if you have multiple generator connectors in parallel, it's the same thing, right? And the total amount of active power, reactive power, and apparent power would be the sum of all turbines. That's it. Theory-wise, it's pretty straightforward and simple. And today, we are only focused on power loss-based equivalencing on power flow models. You will see that even though the method is power loss-based, the equivalence model can also be used for short circuit study, and we will demonstrate how accurate the result would look like. In the future, we will be talking about the stability model related equivalizing, like power plant controller and also harmonics as a future advanced topics. Now, some people may want to ask why we use this power loss-based method, why we do not use Thevenin equivalent, right? Because I stopped myself from saying Thevenin throughout the presentation to just avoid confusing, because some people use Thevenin equivalent. My take on, or my takeaway of this method is as follows. It's because FERC has an order, which is FERC Order 827, stating that any non-synchronous generation needs to provide a dynamic reactive power within the range of 95 lead and lag at the high side of the generator substation. What does that mean? That means if you have certain amount of inverters generating, let's say 10 megawatt at the terminal of the inverter, what utility company and the FERC and also those regulatory entities care about is what you can provide at the point of interconnection. So if the loss you have from your one line is not equal to the loss you will have from your equivalent circuit, if they are different, then the active power calculated from the lumped model at this point would not be equal to what you got from a one-line model, including active and reactive. So if your active power is missed or is deviated, at the same time, your reactive power should be deviated as well, because that deviates your requirements, number one, and the second, your capability, right? So you need to make sure that the loss you got from your one-line design is equal to the loss you have from your equivalent system. So that's my take on of why we are using power loss-based equivalency, but not Thevenin equivalence. That's pretty much it for my theory introduction or theory review. There are quite a few references that listed here, which we can find out from the website of WEC, Western Electricity Coordinating Council, and NREL, National Renewable Energy Laboratory. So they are all public, and they have described this technology as a requirement in details. When you come into each RTO ISO, they may have different requirements, but the principle is the same. So those documentations are really good references for you to come up with your different equivalized model for different purpose. All right, so hopefully we can keep our minds refreshed about the theory. I will keep these slides open, but we will switch to EasyPower to have this live demonstration of how to calculate. Sometimes we need to go back to the presentation to know the theory and why we are doing that, but let's just do the live example to show how it's calculated. So I'll go to my EasyPower. I already have a case with the utility photovoltaic 40 megawatt detailed design, which is a one-line design. So let's convert this one line to the equivalized lumped model. Oh, I already have it open. Sorry about that. I should have this closed. I don't want to change anything. I need to close this as well. Okay, so let's edit it. Now this is my one-line design, nothing else. In this one-line design, I have 20 inverters. All right, each of them is rated at 2.2 MVA with 2 megawatt generating active power, right? And I have my GSUs. I have my collector system. So you can see the right-hand side, the bus A side, you have 5 inverters connecting radio in parallel with another 5. And another hand side, the bus B side, you have 10 inverters connecting in radio. It does not connect in parallel at all. You need to go through the whole collector system to hit the last one. So it has different configurations. We will show that this calculation method can handle many different situations, because all you need is to know the circuit impedance and the active power flowing through it. To calculate, I think the easiest way is to use Excel, at least based on my experience. And EasyPower provides us a very convenient way to dump the database to Excel spreadsheet. So let's take advantage of that database browser. All I need is my cable data. So where is my cable? Here is my cable. Now I can open with Excel to dump all the cable information into Excel to let me run the calculation. And I have already dumped it here. This is just dumped. So what information I need? I don't need those IDM status because I know they won't affect my calculation. All I need is the impedance and the MVA rating. The active power flowing on the circuit, right? So I don't need to know the unit. I definitely need the length, because that multiplied by the per length impedance would give me the actual impedance on that circuit. I don't need all this information until here, and I don't need all this information until here. So let's delete all of them for the sake of clarity. One thing we need to notice that what EasyPower provided is the capacitive reactance. Remember from our equation, switch back to the slides. What we need is a sum of charging, which is a susceptance, but not capacitive reactance. So the first thing we need to do is to convert the capacitive reactance to charging, right? So we need to put a B1 here, or B0 here, and it's easy to convert because the susceptance is just the inverse of the capacitive reactance, right? I can do it here, copy the equation here. Okay, let's do it. So this number is my per length, 1,000 feet charging. So I need to use this charging multiplied by 1,000 to get my real charging. Now let's take XC and XC0 out of the picture, hide them, and let's calculate the parameter of the line. Now the resistance would be equal to resistance times length divided by length unit. It's 1,000 feet. I need to fix this cell as E2 because everyone would use it, so don't shift it. Say it's always E2. It's always E2. What's my charging? My charging would be the charging per 1,000 feet times length. I need to fix this as well. Divided by 1,000, right? Same to my B0. Now that's the calculated impedance or the charging and charging for this circuit. Now we copy the equations down below. Okay, I got all my impedances. Remember, what we need furthermore is the active power flowing through the circuit. So we need to find that out and fill that into the equation. So I need to create another column here, which is P in megawatt. And then let's go back to EasyPower one line to check how much active power flows through each circuit. So from collector 1A to collector 2A, from the design, you can say have 8 megawatt because I have 4 inverters as my upstream inverters, right? I have 6 here, 4 here, 2 here. For my collector 6A to 7A, the same topology would apply to 6, 8, 6, 2, 4. From collector 1B to collector 2B, I think it's on the other side, the left-hand side. 1B to 2B, I got 1, 2, 3, 4, 5, 6 inverters. So here is 12 because I have 2 megawatt per inverter, right? So 2B to 3B, okay, I got another one, I got 14, 16, 18. Collector 6B to 7B, which is this collector, I have 4 downstream or upstream, depends on perspective. 8, this should be 6. 8, 9 should be 4, it should be 2. That's it. From the bus A to collector 1A, I got 10 inverters in total, so my megawatt is 20. Collector 1A to collector 6A, I got 10 here. Bus B to collector 5B, I got 20. Collector 1B to collector 6B, I got 10, right? 1, 2, 3, 4, 5 times 2, that's 10. Now I got all the information I need, and I definitely don't forget to put the P total here. That's 40, because we know that already, right? That's all the information we have and all we need. So now we need to plug in the formula or the equation to find out what exactly my collector system equivalent looks like. Step 1 is that we need to make sure I got it right. This is my R1 times P squared, X1, R0, X0. I don't have to do that for B because line charging is just simply add up, right? So my resistance would be R1 is equal to the real R1 times P squared. Now I need to keep locking this E2 column to avoid shifting. This B is equal to this B directly, right? I need to copy this equation as well. Now I copy all the equation down. Now I have my product of P squared times each item. Now let's sum them up. So I'm calculating my sum product. Let's just do it here. Total is equal to sum of all the product, right? I think I can cross the boundary and do this, yes, because it's already a sum. Now you got the total loss actually from this item. What you need to do is to divide by the P total square to get your equivalent model. So we got our equivalent R1, X1, R0, X0. What we want here is XC because that's XC I want to put back to EasyPower. No longer charging, right? XC0. And my R1 is equal to this sum product divided by my P total square. Now I need to lock this cell because everybody will be using that. And I copy my XC is equal to 1 divided by charging, right? It has nothing to do with power, but just charging. Okay, I got my equivalent. This is the number I need to put back to EasyPower as an equivalized model. And what we need to do next is to build my equivalized model, the lumped model, and run the power flow study and the short circuit studies to compare the result between the power flow result and the short circuit result between the one-line model and the lumped model, equivalized model, right? So what we do here is copy utility bus and the main power transformers because I don't equivalize them. I only equivalize equipment downstream. So they are the same. Now I put a bus here, 34.5, put another bus down below, put a cable, which is my collector system equivalent between them. I should connect from here. Okay, so let's connect from here, connect from here. Okay, that would change all the per unit voltage base. Now, what's my parameter entered? Keep in mind, this is my R1, so I put it as my R1, X1, X1, XC is here. That's my XC, R0, R0, X0, and XC0, right? Just copy and paste. Now, keep in mind that the impedance entered here is almost per 1,000 feet because we wanted the exact number, so the length should be 1,000 feet. That the per length impedance would eventually be your impedance of the cable. Makes sense, right? So let's click on OK. Okay, I'm done with my collector system equivalent. Now let's go to the transformer. Like we said before, we can copy and paste the transformer here without changing the impedance. But what we need to do is to raise the MVA rating and MVA base by 20 times because we have 20 GSUs connecting parallel, right? That's 46. This is 46 as well. Don't touch the impedance because they are consistent. Okay. And then I put another bus here. Copy this generator here as well. I don't have to touch anything to my synchronous transient and subtransient impedance at all. All I need is just to raise the MVA by 20 times. That's 44. And my power flow, change this to 40. Now I do need to change the reactive power as well because that's 0.66 multiplied by 20 times, so which would give me 0.66 times 20. That's 13.2. Okay, so I have negative 13.2 and the positive 13.2. Right? Is anything wrong? Guess not. Okay, so this is my equivalence model. Let's compare the performance. Let's compare the power flow study result between those two models. And what we care about is the active power delivered at this point at the utility bus, right? Between those two models. So let's just run the power flow. To run the power flow, we have to first deactivate the equivalence model and then run the power flow. Now the power flow result looks like this. We need to keep in mind about this number. So let's just take a snapshot of those. The 39.690 is the active power delivered at the utility bus, a high side of the substation transformer. Let's say if we can get the same number from our equivalized model. So take this, deactivate, activate this, run the power flow, solve. Please forgive me about the collector system ampere rating. The ampere rating of the collector system equivalent is meaningless because it's an equivalent circuit. It does not have any rating at all. It's not practical. So the rating of each cable is already predetermined by your design. So when it comes to the equivalent cable, it really doesn't matter. So, but for the sake of clarity or the easement, I will just set as 99999 to avoid any overload. Oh, fine, it is okay, doesn't matter. Solve the power flow, solve, okay. What's the active power and the reactive power delivered at the utility bus from my equivalence model? 39.691. If we recall, this is what we got from the one-line design, detailed one-line design. You can see the active power is just 0.001 megawatt different. The reactive power is just 0.005 megavar different. So I would say it's close enough, right? It's within even within 0.1% difference. Now, we kind of understand that because the assumption we made is that the loss across the collector system equivalent and the GSU equivalent is the same. So same generation, same loss, of course you get the same result, right? How about short circuit? Let's run a short circuit study at the low end of your main power transformer, because in that case, we can only calculate the fault current contribution from your equivalent downstream or upstream, depends on perspective, right? To see how much current flowing into this bus one if you place a fault here. And then compare that with the fault applied here in your detailed one-line design to say what's the fault contribution. And then we can tell if the fault contribution is the same, right? So let's do that. Apply a single line to ground fault, fine. Doesn't matter here, three-phase or single line. Okay, if we apply a single line to ground fault here, there are 492 ampere coming from the generators or the inverters. So let's take that down. Now let's go back to the database. Let's deactivate the equivalent model and activate the one-line design. We go to short circuit, apply a fault here, the same single line ground fault. What we got? We got 246 and 246. So if you add them up, 246 plus 246, that's exactly 492 ampere. So the model gives you exactly the same amount of fault current contribution between the one-line model and the lumped model, which is satisfactory. Very good, right? So we compared the performance of the power flow study result and the short circuit study result between the one-line model and the lumped equivalence model. They are pretty much the same or exactly the same. That's good enough. That's satisfactory. Good. Now let's talk about some special cases, or actually the more meaningful cases where you don't have the same inverters in your plant. This is too ideal that you have same inverter in your plant. In your actual design, you may have a couple different inverters. Let's say you may have different inverters for the inverter 1 to inverter 5. Let's say you may have a 4 megawatt. What you're going to do? You have different inverter, you have different GSU. What you're going to do with that? Because you cannot use a lumped equivalence generating to represent all of them, right? Their MVA rating is different. Their subtransient impedance and transient impedance are different, maybe. And also their stability model are different. So you cannot use one unique generator to represent all of them. Now, this concept introduces the concept of grouping, which means that we need to model different types of inverter using different types of lumped equivalent. So as if there are one type of inverter, you have to use one equivalent generator. If there are two types of inverter, you have to use two inverter equivalent. If there are 3 types of inverter, you have to use 3 inverter equivalent, and so on. So each type of inverter would be represented by each lumped model. That's the principle, right? So that's called as grouping. So let's go to another case that I have already created before to show how that looks like. I have a 50 megawatt case, which is exactly the same with the 40 megawatt case, the solar design, but I replaced the inverter from 2 megawatt to 4 megawatt on inverter 1 through inverter 5A, right? So I have 2 groups, 2 types of inverter. So what we need to do is to use 2 lumped inverter and pad mount transformer equivalent to represent each type of the inverter and aggregate the total amount of generation from each type together to get your equivalized generator. Make sense? For instance, I have 15 2 megawatt generator. So what I have here should be a 30 megawatt, 33 MVA rated generator, which is a case. Now I've already created a case before for the sake of saving time, but we just walk through the parameter settings to make sure it's consistent, right? So I think the reactive power here should be 0.66 times 15. So that could be give you 9.9, right? Impedance does not change. Specific does not change at all. The power factor actually doesn't matter here. And for the another hand side, for the 5 lumped model, so each inverter is 4.4. 5 of them will give you 22, right? The power flow, you got 20, because 4 times 5 is 20. For the reactive power limit, that would be use the same amount. That's fine. We can do the same thing. So let's do the math. 0.66 times 5, 3.3. Okay, so we need to enter 3.3 here and 3.3 here as my equivalent model. Now, GSU is the same. You can see that impedance is the same. I just changed the MVA rating by 15 times for the 2.3 MVA transformer. For the 4.6 MVA transformer, I multiply by 5, get my 23 MVA rating, and the base, I don't change the impedance at all. That should be it. How about the collector system equivalent? By comparing this 50 megawatt design with 40 megawatt design, we know that we don't have any topology change. We don't have any impedance change of the circuit. The only thing have changed is some power flow through some circuit, specifically from bus 1A to collector 1A, collector 1A to 2A, 2A to 3A, 3A to 4A, and 5A. So we can use the same spreadsheet, but just change the power flow on each circuit of the ones who has been modified to come up with my new collector system equivalent. Now you can see the difference here. Let's take a snapshot of what's before. This is our 40 megawatt equivalence, right? So let's just change the megawatt and see what has been changed. So you got a 16 here, 12 here, 8, 4, and eventually you have 30 megawatt and you have 50 megawatt in total, right? Because anything related to collector 1A and the upstream needs to be doubled because you use 4 megawatt, and P total needs to be changed to 50. Now this number is for the 50 megawatt design, which is different. You can see not so much difference, but it's still about 10 to 20% deviation deviation or difference. Yeah, it's okay. So we need to enter the new equivalized circuit impedance into this equivalized circuit here. And I think I've already done that for the sake of time saving. We just need to compare to make sure it is right. Okay, 5019, okay. X1, okay. XR0, okay, X0. X and X0 never change because that's irrelevant to the power flow. That's only relevant to the impedance, the cable connectivity and the length of the cable, right? Okay, I got it right. So let's compare the performance. For a 50 megawatt design, let's run the power flow first. Run the power flow. Please forgive me, I didn't change the design at all. I keep the same impedance and rating for the sake of comparison or for the sake of easement of changing the turbine size. In the real life, if you change your inverter size, definitely the circuit, collector circuit needs to be changed, right? That's a very natural thing. So the amount of power I can deliver at the point of interconnection is 49,596 megawatt and 6.256 megavar. That's from my one line power flow calculation result. Now let's go to the lumped equivalence model to see what number we can come up with if they are the same or how much difference we can observe. So solve the power flow, compare 49.596, 49.596, exactly the same. Reactive power 6.256, 6.260, close enough, less than 1%, 0.1% actually. So, okay, this is the right model we should be using. If the utility was asking you, hey, what's your equivalence model? You give them, this is my equivalence model. Loss is the same. The amount of active power and reactive power I can deliver at my point of interconnection is the same as my one line. And you can use this for power flow studies. Oh, short circuit. Yes, let's do it again. Short circuit. Here, let's say we apply a three-phase ground fault, just a different fault to see if they're the same. Okay, three-phase ground fault at the low side of the main power transformer. 870 comes from the inverters, right? So let's switch to the database. Deactivate the equivalence model and activate the real one line. And let's run a short circuit. Apply a fault here, bus A, because that's the low end of the main power transformer, right? Same location. So apply the same fault, three-phase ground. How much current I got in total? Do the math. 348 from B plus 522 from A. I got 870. What I got from my equivalence model? 870. Okay, perfect. Total current contribution, total current fault current, 9,073. 9,073. It's exactly the same. Perfect. So, like we introduced before, even though this method is power loss based, you can also use the same model you come up with for the short circuit study and short circuit models. In the future, we'll introduce this model if you just replace the stability model from the different inverters into the lumped inverter. It's going to get the same performance or response. But those things will be covered in the later on webinars. Please pay attention to our webinar series. We will introduce that later. I think that's pretty much it. We have covered the theory of equivalizing. We have used a live example to demonstrate how to calculate using Excel. You dump the data into Excel spreadsheet, just calculate or gather information about active power flowing through each circuit and use a formula we introduced in the PPT in the presentation and calculate your collector system equivalent. And the same story applied to GSUs and generators. Hopefully, it's not that difficult to understand. It's not that difficult to replicate. And hopefully it's useful in your future engineer works, especially at the time where you need to interact with your utilities that this plant is connected to. Thank you very much. That's pretty much it for me today. Please feel free to contact me. My email address is tao@easypower.com. I think Jim can share with you my detailed contact information if you need it. Please let me know if you have any questions or comments, anything we can help with, or any future topics you have interest in and you think I can present. Feel free to contact me. Thank you again.
Thank you, Tao. I'm going to open up Tao's microphone, and there were a couple of questions that came in that probably worth talking about. So, Tao, if you'd like to take over.
Yeah, thank you, Jim. Just want to make sure, can you hear me okay?
Yes.
I'll try my best to answer as much questions I've collected through the questions dialog box of this webinar. So one thing, actually, quite a few audience asked is that the method to create the impedance of the inverter and the PV or wind source impedance of the short circuit studies, which means that the question is basically asking how to come up with a generator short circuit impedance for a PV solar farm and wind source or wind generator for type 3 and type 4 in general. So this answer can be two parts. A simple answer would be that usually the manufacturer of the PV or wind farm or wind turbine would give you the maximum amount of fault current, let's say 150, 130, 110% of the full load ampere, right? So use that number as the fault current you will have or you will get from the generator. And then you can use Thevenin equivalent to back calculate what's the V source of your generator, supposing your generator terminal voltage is 1 per unit, right? So that's very straightforward. It's just a backward calculation based on the available fault current to get your fault impedance. That's a simple answer. Now, I know many audience, especially some experienced audience will say, no, that's not the case, because during the fault, the impedance will change or the fault current amount will change. IEEE 24 working group, and also actually a lot of like NERC fault current study groups, working groups are working on and have come up with a new model last year and also this year, which is called as voltage controlled current source, that the fault current from the PV or the wind turbines would be based on the terminal voltage. So which means that it will take an iterative approach, saying that initially, if I use my Thevenin equivalent impedance to get my fault current, and then I back calculate my terminal voltage, and then redetermine what's my new fault current based on this voltage, and recalculate my Thevenin impedance, and recalculate the fault until it converges. So simply speaking, if you just roughly want to say, okay, what my fault current might be to do my breaker duty study or to do my relay coordination, if I know that my fault current might be very different from my operating current, yes, that's typically the approach to give you that rough idea. But to get into the detail, to get into the exact fault contribution during the fault because of those power electronic device, a voltage controlled current source would be required. And it's very similar with IEC 16909 standard required voltage controlled current source. So EasyPower will implement that in our later on versions. But for now, EasyPower can only take the Thevenin impedance back calculated from the available fault current from the manufacturer provided data sheet. So hopefully that clears up the question. And if you have any further questions, please feel free to pop it up through the question dialog. Another question I think it might worth us to answer is that why we cannot use the Thevenin equivalent. Instead, we have to use this a little bit complicated power losses, because roughly speaking, if your only concern is a short circuit study, I don't disagree that the Thevenin impedance of the collector system, let's say you apply a fault as a POI for interconnection, right? You got a fault current, then you back calculate your Thevenin impedance of the equivalized collector system equivalent, that's okay, that works. But that would only work for short circuit purpose. But as you can see from the model, that our model would be utilized in many other studies, such as power flow and stability. In that sense, that model may have some deficiencies because the assumption you made here is through Thevenin equivalent is not consistent that the total consumption of both reactive power and active power throughout the collector system is the same. So that's why utility companies always prefer to use this power loss. And you can see from the presentation that even using the power loss method, you got a very, very close or accurate Thevenin equivalent, right? So that's why typically people prefer to use this method, even though it's a slightly more complicated. So hopefully that answers the question. So I didn't see any further questions pop up. I do want to appreciate your attendance. Thank you very much for listening.
Thank you, Tao.
Thank you very much for listening in. Thank you, Jim.
And we look forward to more presentations in the future from you. Thank you very much.
Sure. Thank you.